In classical digital signal processing, capturing a high-frequency phenomenon is strictly bound by the Nyquist-Shannon sampling theorem. This theorem states that to accurately record a signal, you must sample it at more than twice its highest frequency, placing a rigid limit on digital resolution. If you attempt to track a 771.1 terahertz frequency, the frequency of violet light, you are required to process over 1,500 terahertz of data. Mapping that onto a standard 8,000 index data array requires computer array sizes that are currently impossible to build or process. The Axiom Arc storage system operates outside of this limitation by utilizing a dimensional workaround. Instead of trying to sample discrete physical waves inside a tiny grid, the system abandons physical sampling and maps the frequency to a continuous thermodynamic state. By shifting from digital array constraints to thermodynamic mapping, the system attempts to move past traditional information theory limits. This mapping relies on the Thermodynamic Angular Symmetry Limit, or TASL. TASL is the mathematical engine that calculates exactly how much data density a specific frequency can hold based on its temperature and angular displacement. To function, the system maintains a strict baseline invariant. The total block energy is held constant at 383.99 joules. Because the total energy is fixed, the system divides Avogadro's number, a constant representing 6.022 times 10 to the 23rd units of a substance, by the physical energy of the targeted photon. For violet light, this calculation allocates exactly 801.32 bits of informational weight to a single energy unit. To test this quantum data bridge, we will analyze 3 empirical stress tests, comparing how the system handles high-entropy fractal images against low-entropy gradient images. If data structure and thermodynamic phase states are proven interchangeable on a geometric lattice, it suggests a new path for file compression. Test 1 establishes our control group by running the canonical's storage grade system using its base dimensional reduction core mappings. A dimensional reduction core, or DRC, is a geometric mapping unit that aligns data into a specific rotation path to achieve compression. In this baseline configuration, the system should handle simple, low-entropy data efficiently. This readout shows the Test 1 gradient output, achieving a 64.25x compression ratio and a 54.15 decibel PSNR. PSNR measures the reconstructed image's quality against the original. Looking at the difference panel on the right, the dark, fine-textured mesh indicates near-perfect structural similarity. We then shift focus to see how this baseline handles complex, high-entropy fractal data. This readout shows the Test 1 fractal results. It achieves a 21.87x compression ratio, and the PSNR drops to 28.73 decibels. The difference panel here reveals heavy, visible distortion patterns throughout the fractal's reconstruction. While Test 1 proves the basic viability of the system, the noisy fractal output indicates that the baseline canonical mapping limits the framework's capacity. Test 2 removes the safety bounds, shifting the architecture to a non-storage, in-memory holographic variant. This variant deploys an aggressive TRLE v2 protocol to rack high-entropy spectral signatures into pre-computed hexagram triads. TRLE stands for Thermodynamic Run-Length Encoding, a process that compresses data by identifying identical thermodynamic state sequences instead of scanning raw bytes. This readout shows the Test 2 fractal compression, achieving a massive 992.97x compression ratio. Despite this extreme compression, image fidelity actually improves over the baseline. The PSNR jumps to 46.30 decibels, and the difference map shows a perfectly clean structural reconstruction. This defines the entropic compression paradox. While traditional compression efficiency drops as data entropy rises, Axiomark's efficiency increases at high entropy because the system requires complexity to orient its lattice. But there is a flip side to this paradox. We must observe what happens when Axiomark is fed data that is entirely devoid of complexity. This readout shows the Test 2 gradient image experiencing a catastrophic failure. The decompressed image is purely black and corrupted, resulting in a flat 1.00x compression ratio. A perfectly smooth gradient lacks the distinct prime lock spectral anchors that the lattice uses to orient itself. Without those anchors, the phase vectors drift and the thermodynamic structure collapses. The engineering problem is how to reconstruct a low-entropy thermodynamic state once the visual data has collapsed. The solution adapts mathematics developed in astrophysics for the detection of gravitational waves. Facilities like LIGO use continuous wavelet transforms, or CWT, to locate specific frequency chirps hidden inside background noise. CWT is a mathematical tool that analyzes signals across both time and frequency simultaneously. Axiomark's new Graph Finder Hydration Manager adopts this CWT logic. It scans the vault's elliptic curve spectral signature until it locks onto a hidden prime lock signal. Even when the visual gradient collapsed to black, its underlying spectral identity survived within the system's index. When the system detects a spectral mismatch, it triggers a reassembly of the data directly from the canonical lattice. Treating data loss identically to a missing gravitational wave provides a predictable error correction mechanism for low-entropy data. Test 3 evaluates the final implementation, the storage-grade environment augmented with active spectral index and gravitational wave retrieval protocols. This readout shows the successful resurrection of the Test 3 gradient image. The visual data is restored, achieving an 18.62x compression ratio. In the difference map, we observe a jagged diagonal wave pattern. This artifacting shows the CWT patch is actively rebuilding the lattice structure. We then evaluate how this continuous background scanning affects the high-entropy fractal data. This readout shows the Test 3 fractal results. The system maintains its 992.97x compression ratio. However, the PSNR drops to 39.98 decibels, and the difference map is visibly darker and noisier. This is the thermodynamic cost of the constant background prime lock scanning. Test 3 proves the system can preserve extreme compression for complex data while maintaining survival for simple data through constant spectral validation. We have moved from a canonical baseline to an unrestrained holographic limit, and finally to a stabilized retrieval system. This chart shows compression ratio versus signal-to-noise ratio across the tests. We can trace the gradient's recovery path alongside the fractal's jump to the 992 times threshold. The system achieves 992 times compression strictly by indexing the entropy within the fractal pattern. These results indicate that data structure and thermodynamic phase states are interchangeable within this framework. In this context, the Nyquist limit ceases to be the primary barrier, as the data is no longer sampled as a discrete wave. Ultimately, the Axiomark system requires the inherent complexity of the universe to maintain information density, rather than being limited by it. By mapping information density directly to physical laws, these tests demonstrate a functional path for holographic memory systems.